like
Or the fish and chips place.
Yeah,
that's
don't
the
eat
apple.
potato.
Okay, so
I keep mine.
here's kind of our plan. So here's how we're gonna do this. I'm gonna let you finish up this assignment over the book assignment stuff, right? I'm gonna put up I'm not gonna require it, but I'll put up a practice test that has some corresponding kinds of problems online. And then the next test you're gonna do is gonna be, I think I'm gonna do one paper and pencil question, and I'll do most of it online. The paper and pencil question, I wanna see one table. I wanna see, build a table all the way through, but the rest of them I'll let you do online. Because the one after that's gonna be paper and pencil, right? The one after that's gonna be on optimization, and that's gonna be all paper and pencil, okay? So just be aware. I wanna introduce the optimization stuff though, and just get you kind of thinking about this a little bit. We'll come back to it later, and I'll give you a sheet that gives you detailed procedures, but I want you to just kind of, while we're in the midst of doing all this table stuff, it's a good time to think about the optimization process. So this would be an easy problem to do, right? If I said find all the relative extrema, that would be a piece of cake, right? And we're getting to the point where we can do a lot of different functions, as long as we have a function of a single variable. If I were to graph this thing, what's it gonna look like? Yeah, I mean, in this case, it's a parabola, right? But we want to think in terms of a graph. I'm going to have the function is going to be graphed on the y-axis, and I've got a single variable on the x-axis. And so in this case, I'm going to end up with, something, we don't know where it is, but it's going to do something like that, right? And if I want to find the relative extrema, well, this one would be right there. That's going to be at the minimum of that parabola, at the vertex, okay? All right, so we're shifting gears massively here, right? This looks like a totally different situation, but our goal is we want to take these applications, and this is a really fun part of calculus. It really is. Optimization is where we're going to try to use our analysis skills that we've been developing, including calculus, to apply it to a situation where there's a useful purpose for either minimizing or maximizing a function. Okay? Like, for example, let's look at this one. A manufacturer wants to design an open box having a square base in a surface area of 108 square inches. Who knows why? Maybe that's impacted by the weight or something. The shipping weight needs to be a certain shipping weight, and he's using plate steel, and so he can only have so much area of the steel, right, in order to keep the weight minimum, okay? He wants to know what dimensions will produce a box with maximum volume. So for a fixed surface area, what dimensions are going to give us maximum volume? That's pretty cool to be able to do that, right? These kinds of problems would have been extremely difficult and typically impossible to do without calculus. Okay, so what can we do here? Suggestions. We want to somehow turn this into a problem that we know how to do, right?
So, it's kind of, this might be really obvious, but imagine once you'll get like a graph that shows like more weight.
Well, you're thinking that
Yeah.
you're thinking the right thing.
You're gonna get a graph with a function that's gonna show the amount of volume and it's gonna have maximum. But then once you get past it with like the like surface area or whatever, because it's gonna keep constant.
Right, so you're going to want to find that sweet spot on the curve where we're going to get the maximum volume, right? Okay, so what can we do with this, though? They gave us a nice picture here. What is the quantity that we're trying to maximize?
Volume.
Volume, okay. All right, so we want to come up with then some kind of a volume equation that we can work with. Agreed?
Yeah.
Okay, so here's our picture. We've got variables x and h, it looks like. Okay. What is the volume in terms of x and h? X squared times h, everybody agree if I have a square base?
Yes.
Okay. So we can come up with a volume equation. Volume of x and h, right? That looks a little weird, but that means a function of more than one variable is equal to x squared times h. Okay, that doesn't look like that, right? What's wrong with that?
Two variables.
Yeah, I got two variables, right? And furthermore, this is, if you just said, okay, the volume is x squared times h, and we want to maximize the volume, I got an easy answer for you, infinity. I'll just let the box be infinitely big, right?
But you
So
can't
we
get
have
the surface.
Isolate H.
Yeah, so they did give us a constraint here though, didn't they?
Yeah.
They gave, and the constraint is always gonna be some kind of a number, right? They gave us a constraint, they told us that the surface area has to be 108 inches,
Yeah.
okay? So can we do two things at once here? We want to impose that constraint on our situation, but we also want to turn this into a function of a single variable, right? We don't know how to do calculus with multiple variables. That's in your futures, right? That's next year. Okay, we don't know how to do that at this point. So this doesn't look like this, and in fact, we can't even deal with this. We don't know how to take a derivative involving multiple variables, right? Okay, so what is our surface area equation of that object?
4 times, or 4x8.
Okay, everybody agree that the lateral sides are all the same, they're all x by h, and there's 4 of those, plus,
Plus x times x.
yeah, plus x squared for the base, okay? So area, surface area equals x squared plus 4xh, okay, and what's that equal to?
108.
Ah, that's useful, right? Now, what could I do? Think about
Do
this.
you want to solve for H so that?
Everybody see that? So I got some options here. Theoretically, I could solve for either x or h in this equation and substitute, right? And then I'm gonna get a function of a single variable up here, right? But we gotta be smart about this. It'd be hard to solve for h, or for x, wouldn't it?
Yeah.
It'd be real hard because x this function is quadratic in x, shows up in 2 terms, right? The h, easy, right? There's a single h there, so it's easy to isolate. What would the steps be to get that h by itself? What would first I would subtract x squared and then,
Divide by 4.
okay, so we can do that. So we get h equals 108 minus x squared divided by 4x, right? And I'm gonna put a box around that immediately, and I just got in that habit early on, it's very helpful. Whenever I have a substitution equation, put a box around it, because typically you wanna be able to come back and find that later. So that's gonna be what we substitute, and that makes things much, much better. Then we end up with volume as a function of x, because I'm substituting x's for the h, is gonna equal x squared times all that stuff. 108 minus x squared over 4x. Right, and look, I can do some stuff now that's helpful. I could cancel an x top to bottom, and then just distribute that x, right?
Yeah.
And so I'm gonna get 108x over 4 minus x cubed over 4. So I could pull the 4 out front if I wanted, the 1/4. I could, yeah, do that. And if I want to write it in factor form, if I wanted to, I could write it as x over 4 times 108 minus x squared. Okay? That looks better, right? Doesn't that look a lot more like what I'm used to, right? Okay, so what were my, now we can pretty much almost just flip into math mode, algebra mode, or calculus mode, and crank out some calculus. What were our steps here? You had a lot of practice with this. What are our steps to analyze this function? And honestly, this, I'm not asking as much here as I typically am in the stuff you're doing now, right? I'm not asking for everything. What are we looking for here in this problem specifically? Looking for just a maximum, right? Right, so all I'm looking for is a maximum. I don't even necessarily, if it's not convenient, have to take the second derivative here. If it's convenient, I will, right? But if it's not, I won't even bother. Okay? So what do I do?
Oh, well, you're going to use these functions for product.
Okay, but before I even differentiate, there's something I want to do. Gotta get the domain, okay? Now, the domain, talk to me about the domain for a problem like this.
You can't have.
Okay, how come? You're right.
Because you can't have a negative.
Ah, okay, so there's gonna be two components to the domain. There's the mathematical part, right? We can't, the domain is gonna be restricted mathematically by whatever function we have potentially, right? But then there's also gonna be some restrictions on the domain imposed by the fact that this is not an abstract problem. This is a real problem, right? A physical problem. So we have to adhere to reality here, right? And sometimes math is going to give us a domain that may not always be physical, okay? So mathematically, there's no restriction on that domain, is there? No, there's not, right? Everybody agree? Okay. Physically, there is, right? One restriction is that x has to be non-negative, right?
Yeah.
Okay? There's another one too, though, and this is the part that sometimes people have to kind of get their thinking straight on this. There is going to be an upper limit too here, right? Go ahead.
See.
X squared can't be bigger than 108, exactly. Now, there were two variables that we started with, x and h. Agreed? So almost always what's going to happen in situations like this, and in fact, if it doesn't happen this way, it's a non-problem, because then there's going to be some, it doesn't really, like infinity could be an answer or 0 could be an answer. But almost always there's going to be an inverse relationship between the independent variables that feed into the quantity, the function that we're trying to optimize, right? So in this case, wouldn't you agree that if the surface area is fixed, as h gets bigger, x gets smaller, right? And as x gets bigger, h gets smaller because of that constraint, right? And do you kind of get a sense here already that if there weren't that inverse relationship, this is a weird problem then, right? It's not something that we don't need calculus for this, right? So then what could we do with this? Okay, if we're talking about the x's, the minimum x would be 0. And do you even include 0? And that's a legitimate question. If x were 0, what's the volume going to be? 0, right? So we don't even really need to include 0. That's obviously not an answer. But we want to pick, so we need values bigger than 0, okay? The upper extreme for x, here's a good way to think about this. X is going to be maximized when h is minimized, right? So the smallest physical value that h could have would be 0, right? So when h goes to 0, you kind of want to think about this almost like play this cartoon in your head. As h gets smaller, the base is going to get bigger, right? And in the extreme, when h goes to 0, this open box just becomes a flat piece of metal. Once again, what's the volume that holds? 0, right? When would that happen, though? H is going to go to 0 when x is what? Well, take this equation right here. So look, we put a box around this, and it's helpful. If I let h go to 0, that tells you the answer right now, doesn't it? Right? Because if h goes to 0, then the top of that fraction would have to be 0, and x squared would have to equal the square root of 108. Everybody see that? Okay. So our domain then is going to look like this. Right?
Yeah.
Okay. Now we got our domain, we got our function, we just do some calculus. It's not very hard calculus. And that's the other nice thing about this, is once you, I've really worked you hard on doing these tables, but once you get into actual optimization problems, very seldom are they going to be as hard as the problems you're doing now, right? They don't always have to be. Usually they're going to be pretty easy stuff like this. Okay, so if we differentiate, probably just differentiate here because we've got it written as a polynomial. We don't want to do here because it's a product. The product rule is harder, right? So v prime is what? I can leave my 1/4 out front. What am I getting?
X
if I'm differentiating, what's the derivative of 108x? 108. Derivative of x cubed? There you go. Okay. And I could factor another 3 out of that, couldn't I? And get 3/4 times 36 minus x squared. Okay. So what's my what are my critical numbers?
6.
When x equals 6 or x equals -6, but -6 isn't in our domain, right? So 6 is the one critical number we get. Do we want to take a second derivative here?
No.
I would. I mean, you don't have to. How come I would say it probably makes sense? So easy. So easy to do. Yeah. Look, if we take the second derivative, and I get 1/4, derivative of 108 is 0, right? The derivative of -3x squared is -6x, so I'm getting -6/4, which is -3/2 x. Okay? Now look, our table is going to be super easy on this one. All we need is a little bit of space down here. So our domain goes from 0 up to the square root of 108. We only had one critical number, which was at 6. That was a 0 of the first derivative. And at any positive number, what's the sign of the second derivative? Negative. Well, what's that tell you? Yeah, I got a horizontal tangent line with a negative concavity. So there's our maximum, isn't it, right? How easy is that, right? And what are they looking for? Dimensions, right? So there's x. All I got to do is once again go back to my box and find h, the substitution equation. You get when we do a substitution equation, we've already solved for the other variable in terms of x. All the work's already done. So if I plug 6 in, then we just get h equals 108 minus 36, which is what, 72 over 24, so it's 3. So there's my dimensions, right? Height is 3, and the width of the base is 6. Done. That's pretty cool, isn't it? So we can do that. Okay? All right, there's your first taste of optimization. So be finishing up this assignment. I'll put up a practice test, and we'll take a couple days next week to. I want to make it. There'll be a small written part.
So it's like online and written.
And then I'll do one, like probably just one. I want to see you guys do one table, but otherwise I'll let you do online so you can retake it more easily.
Sounds good.